Hi guys. So initially I planned about making video on max flows and things like that. But then I kind of realized that we already had logic in Ancestor. We already had some other topic about graphs. Sure what it was, but we had like several topics on graphs. I think shortest path, right. Uh, it's kind of not very logical to cover all complicated topics first. So, and maximum flows are for sure like not a beginner friendly topic. So I decided to make something easier, some more introductory to graphs, because a lot of people initially struggle with graphs a little bit. I was among them, and I believe I'm still somewhat among them, but at least I am. Now, learning from like easier things helps a little bit. So that's why I decided to make a video on something as simple as depth first search. That if you look deep enough into this topic, you will find a lot of non-trivial things that you can do with DFS. So let me first do like some very quick introduction, just in case you don't actually know what depth first search is. No, not like that. I'd actually like it more. Okay. Yeah, so unfortunately I had to change my setup a bit. But we'll figure everything. Right. Now it's more like it. So DFS. Now, before we can actually talk about DFS, it makes more sense to talk about what is a graph, right? I believe you heard like vertices with edges between them or points and lines connecting them, and it's more or less enough on the beginner level to think about a graph just like this. You have several points. Let me make points a bit bigger, with edges connecting them, and it's a graph, right? So why graphs are so important? Because they model a lot of real life things, right? And also because it's easy to construct problems on them. Because a lot of like half of the problems that you can construct on off the top of your head about graphs will be just unsolvable in a polynomial time, I believe. So yeah, a lot of complicated problems exist about graphs, and because of that, a lot of interesting algorithms exist as well. So now one like basic thing that you would like to do about graphs is you want to traverse them. You want to visit each vertex and do something about it. For example, like, look at its neighbors, compute its degree, I don't know, something like that. Maybe the vertices of your graph contain some additional information, like their colors, and you want to check whether or not the coloring is valid. I mean, whether or not the endpoints of each edge are of different colors, something like that. So you can do a lot of things simply by traversing a graph. And there are different ways to traverse a graph. One possible way is DFS. In DFS, we start at some vertex, or potentially we may even have like disconnected graph, right? Several connected components. In such a case, we talk about something like the series of DFS. So we'll start DFS wherever we like can start it. For example, vertices are numbers. This is like number 1, and somewhere on here is number 3, or maybe, yeah. So we will first visit all these components, and we just look through vertices like in sorted order or in any order we like actually. And whenever we see like the current vertex is not visited, it means that it belongs to a new connected component, and we run DFS on it. So, but let's first talk about what DFS does when it encounters one connected component. So it effectively tries to go until it can go somewhere. And because you don't actually know in what order the graph is given in the input, you don't actually know like whether in this vertex you go to the right or to the left. That's it. If your problem is solvable with DFS, it usually needs to like not care about the specific order in which you traverse the children of a given vertex. Once it can't go anywhere, so there are no outgoing edges, it goes back to the previous vertex. And there are several ways to do it. One way is, of course, recursive. You just call DFS of vertex, and it also knows some state. So it knows the recursive stack, like what DFS calls led to that call, and it can just return from innermost call and goes to the previous one. But from here, for example, it can go actually this way, right? Because this vertex is not visited. And it can go like here, but it realizes that this vertex is already visited. So it looks at this edge, but it doesn't go there. Okay. So it then returns back, and finds another edge. And it looks at this edge, but it realizes that it leads to a visited vertex. So it retreats to the previous vertex, it retreats further and further. So it resulted in some traversal of a graph. Some edges we've walked along them, and some we didn't. And interesting thing is that if you erase edges that we did not walk along, and what remains is a tree. And a tree is an acyclic connected graph. So first it is connected, so you can go from any vertex to any other vertex. And second, it does not have cycles. And a tree is a concept in like undirected graphs. And so far we were talking only about undirected graphs, but you may encounter directed graphs. It's perfectly fine. Or oriented, sometimes some people call them so. And the algorithm will not differ like substantially. Here we just consider that all lines that are drawn from one node are outgoing edges. And in fact, if our edges were directed, then we'll just traverse outgoing edges, right? Don't look at the incoming edges. So yeah, and that object is called DFS tree. And DFS tree is interesting because you can do a lot of things with it. In particular, you can compute a lot of like helpful values based on what happens in the DFS tree. You can have the classification of the edges. Now, classification of the edges is important because in different algorithms, you want to do different things, but conditions based on which you want to do something are more or less the same. So when we'll talk about implementations, we'll take a look in greater detail at what can happen in DFS. And you'll see that a lot of algorithms that look pretty different are indeed, in fact, more or less the same with the correct implementation, of course. And they make decisions based on type of the edge they encounter. So yeah, let's see what I mean. We'll also have several colors for that purpose. So initially, like every vertex is not visited, right? Let me clear this. We'll traverse it again in the same order. I just want to draw it again to make it clear. Okay, so initially each vertex is not visited, and like, you may be used to the implementation of DFS. It looks something like this. DFS of some vertex V. First, it says like used or visited at V gets true. And then you just look over adjacent vertices. Graph, for example, is like two-dimensional array. Graph at V contains all adjacent vertices of V. And you say like if not visited or not used at V, then you add W. Then you go and recursively call DFS of W. And it's possible, like some problems can be solved in this way, but it's not the most general structure. The most general structure actually, it's not enough to know only about whether the vertex was visited or not. Let me show why. So again, when we first traverse an edge and we visit a new vertex, we say that this is an edge tree, a tree edge, right? Because like when you look at all of these green ones, I can actually, yeah, I can draw lines like this. Nice. So these edges, they form a DFS tree, right? We already discussed that. So it makes perfect sense to call them tree edges. I will even try to, okay, I can't clear that edge. Oh, I just, okay. So these edges form a tree, a DFS tree, and they are called tree edges. These are the edges in which like DFS first visits some vertex. There are other kinds of edges as well. Other edges include back edges. And back edge is, for example, this one over here, and this one over here. And the reason why they are called back edges is because they effectively go back to the vertex that was already visited. Right, so pretty reasonable. They go back, so that's why they call back edges or backward edges, something like this. And so far, to compute like these kinds of edges, to classify them, it's enough to know only whether the vertex was visited or not. But it's not always enough. For example, if your graph is directed, then you can have different kinds of edges. Let's take a look at some example. Let's say that this time, we have a bit different sets of edges. Let's say something like this actually. So, and also we don't need this connected components actually. Second one. So, what happens when we traverse a tree, let's say from that vertex? It's possible that we start with this edge, right? So it will be a tree edge. Then we can't go anywhere because this is prohibited, because we only have this edge, right? So we come back to that vertex and say like, we visit this, okay. And we visit this, and I say, okay. And we encounter an edge that goes back to the vertex that was already like completely processed. And we say it's a back edge. We agreed, all agreed that this is nothing but a back edge. Actually. No, it's not a back edge. Okay. I don't know what I'm talking about. Okay. Back edge is a difference. Huh? Back edge would be something like this. So, and what I previously shown is called a cross edge. We have cross edges, we have back edges, we have tree edges, and there's also forward edge. And you'll see the difference in a second. So, if we are to continue, what would be a what edge? Okay, we would come back from that vertex here. This is a tree edge. And this is a tree edge. So let me get rid of this. Then we can't go anywhere, return. Go here. And here we encounter an edge that goes like this way. And it's a forward edge. Then we go here. It's a tree edge. Then we go here, and I believe it's a cross edge. And the reason why I want to distinguish this is the following. Back edge is the one that goes to ancestor of a vertex on a path from root, right? So that's why blue edge is a back edge. Blue edges, if you look carefully, they create a cycle in a graph. So they go to some ancestor. Let me draw a separate picture. So we have some paths in our DFS, right? From root is potentially higher. And then we have a back edge, something like this. And these 5 edges, they create a cycle. That's why back edges are important. And you may also notice that cross edge is different because it does not lead to the ancestor of the vertex. It leads to simply like already processed vertex. So it does not create a cycle, right? You can't go this way later. You won't be able to go this way because there is no such edge. So yeah, so this is a cross edge, and cross edges are different from back edges because they don't create cycles. And because we have back edges, it makes sense to like introduce forward edges as well. So forward edges is when we go to a successor. From this vertex, we go to successor, but successor was already processed in some other DFS path. So yeah, that's why we also introduce forward edges. Sometimes you can do things in your algorithm based on what kind of edge you encounter. Most usually you're interested in tree edges because you like find a new vertex. Back edges because you find a cycle. You're sometimes interested in cross and forward edges, but I'm not sure that we will look at this. So mostly for the most interested tree edges and back edges. Let me actually show some examples of what you can do with DFS, because so far we only introduced some notation and didn't actually explain why we need it. And it's not a really good practice to do something like this. So one example we already covered, in fact. This example is like we want to find a cycle in a directed graph. It's actually, I think I will break this video into parts or maybe even 3 parts. And first we'll talk about mostly math, so no practice problems in this video, because I found it like kind of difficult to watch 1 hour long videos. So I will break in 2 parts, so half an hour of math, half an hour of implementation details, so that you can watch them separately. Maybe you want to like study first theory, and you want to video only about theory, and then you want to try it for yourself, problems. So you try it for yourself and only then watch about implementation. So yeah, we won't cover like specific problems from the gym, but one problem was about finding a cycle in directed graph, and you can already do this. Whenever you encounter a back edge, you find a cycle. You know that if you start, like you actually have all this paths, all this green paths you have in your recursion stack. So if you were to like append vertices somewhere when visiting them for the first time, then all of these vertices lie in a stack, and you can just take a slice of this stack starting from that vertex, and you get your cycle. So as simple as it gets. But you may ask, like, okay, mathematically, it's clear why back edges are different from cross edges because they go to Ancestor, right? And cross edges just go to some visited vertex. But how do you know whether or not a vertex is an Ancestor? And here is one of the most important concepts comes in about DFS, the concept of colors. So initially, all vertices, let me actually clear all of this and add one back edge that we were missing. Okay. So initially all vertices are white. And the concept of colors, it just extends the concept of visited or not. So visited was a Boolean array. You can do a lot of it, but not everything. And to be able to distinguish all types of edges, you want more than 2 states of vertex. And one common representation of states is colors. Don't have to represent the state of the vertex with a color, but it's common to say that vertices can be white, gray, and I'm not sure that I have a gray color. That's not great. Can we do something? Yeah, okay, great. We have gray color, and then we have like simply black color, right? I'm not sure that black is clearly visible here, but I think like we can actually do something like that. Or maybe something like that. I don't know. We'll see what one is best visible. I actually think that this one was best. At least it's kind of darker than my background. Okay. Actually, we can leave them for reference. So once we visit a vertex for the first time, we say that now you are gray. Now the vertex is gray. Oh, it will be very painful. Now that I think about it. Okay. So once we visit the vertex, we say like, now you are gray. Maybe you know what? It doesn't seem to work quite well. So instead of drawing them, I will do it differently. I will just write a letter next to each vertex, representing like what is the current color. So, and I'll do it in the more visible. So initially everything is white. Once you visit a vertex, you say you are now gray. So we already started you, but we are not done with you yet. And we got to adjacent vertex as usual. So like now you are gray. And there's nowhere else to go. So we say, okay, we are done with that vertex. You are now black. We come back. And we go further. We say like, now you are gray. We can go this way and say you're gray. Now, if you see an edge leading to white vertex, right? Nothing interesting happens. It's just a tree edge. So from gray, actually, you're always at the gray vertex, so it's not really interesting. So to white is tree, right? It's tree edge. If you see an edge to black vertex, it's a cross edge. Because you're already done with that vertex, so it's not an ancestor of current vertex. But if you see an edge that goes from gray vertex to gray vertex, then it's a back edge. Okay, so now we said this edge is a back edge. We are done with this vertex. We then go here. We can go here. We say now you are gray. We then go here. This vertex becomes gray, then it becomes black because there's nowhere to go in this vertex. This vertex becomes black. This vertex becomes black. From this vertex we go here, this becomes gray, then becomes black, and this becomes black. And we skipped one edge, which was forward edge. Don't actually skip them. So this is an edge to black vertex, right? And I said that black is cross edges. That's not entirely true. Now, the correct way to represent it would be the following. Actually, if you see a black edge, black vertex, and it's from vertex U to vertex V, and time in vertex U is smaller than time in vertex V, it means that V is a descendant of U. And in this case, the edge is actually forward edge. And cross edges are edges to black vertices that are not forward edges. And here you can see that we use the concept of entry time to the vertex. That's another important concept. So for each vertex, you can compute entry time and exit time, T in and T out, as we usually call them. And the way to do it is that you just have a global timer or a class variable or whatever you want, or a reference you just pass to DFS. And you just say like +1 every time you visit a new vertex, or every time you enter a vertex and exit a vertex. You got 0 because you entered this, 1, exiting, 2, entry 3, entry 4, nowhere to go 5. You retreat, but you don't exit. You go 6, 7, 8, 9, 10, 11, 12, 13. And one way to check that vertex is an ancestor of another. And so vertex Q is an ancestor of V when time in U is smaller or equal, but actually it can be only equal if U equals to V. It's usually also call this pair an ancestor. So time in should be smaller. Time out of V should be smaller or equal to time out of U. So basically, interval during which vertex V is gray includes, right? It's inside of the interval during which vertex U is gray. So it means that we first visited U, then in some subtree we visited V, then we traversed subtree of V, left V, and only then we left U. So this is a way to check that one vertex is ancestor of another. And there will be that problem in the gym. But these are like basics, what you can do. So you have colors and you have entry and exit times. And they let you do a lot of things. More interesting things that you can find are the following. You can search for bridges, cut points, and strongly connected components. And all of this, and you can also build a condensation graph, but it's more or less the same as strongly connected components. Now the concept of bridges is about undirected graphs. So I'll clear all of this. And we'll see why all of these colors and entry time, exit times, why they matter. I will need a graph, some graph. Let me draw somewhere. Okay, and the graph is undirected, so we have like bidirectional connections. And when you like testing something about DFS, well, one way to do it is you just draw DFS tree first, and then you add like forward edges, backward edges, something like that. Actually, in undirected graph, you can't have forward edges and cross edges. So you just add backward edges. Yeah, and that's why we don't want this. Right. I mean, we don't want this in example because it will ruin the example. So what happens if you run a DFS again and we want to find bridges? And for those of you who don't know, the bridge is an edge. If you remove it, then the graph gets disconnected. It's not a particularly great edge because you don't want to remove it. Actually, why did I need to draw? No, I'm okay with that edge, just not that. It does not look like natural. Okay, never mind. Suppose that we still know like entry exit times. Suppose this time we actually visited this first. And visited this, and we exited this, and yeah, I'll just finish writing this down. We don't need actually this part of the graph. We're doing it. Yeah, let's leave it, but it won't be like particularly important. Okay, so what are the bridges in this graph? Well, let's see. These two are bridges. This is a bridge. Actually, all of this is a bridge. Also, this is a bridge. So a lot of bridges in our graph to find. But how does DFS know about it? Well, if you know entry and exit times, and we already said that you can like classify edges, whether they are tree edges or backward edges, then you can actually determine quickly whether or not an edge is a bridge. Suppose we're currently looking at this edge. Just for an example. Usually we would start looking at this edge and then this, but this edge is more illustrative, I think. So why is it's a bridge, right? Why is it a bridge? Because we know entry time to that vertex, right? Now, what can make this edge not a breach? There is like subtree on this edge, right? This edge is not a breach if there's an edge from that subtree somewhere else, right? But how do we know, like, what is exactly this somewhere else? What if this edge leads somewhere like here? Well, then we will traverse these, and eventually there will be some path to vertex 1, right? In particular, there will be some path to vertex 0, or some ancestor, I should say, of vertex 1. And ancestors of vertex 1 are interesting in that respect that they have enter time smaller than enter time of 1. So if we ever like encounter an edge that goes to a vertex with a smaller entry time than that of 1, then this is not a breach, right? So what we do is like for each vertex, we compute what is the minimum entry time that we can reach from that vertex, not going back through this edge. Now, unfortunately for this vertex, the minimum time is 2. And we can compute minimum time, like if we know what is the minimum time reachable from this and from this, then we just compute minimum of all of this and all minimum of this. So yeah, just a bunch of the same bunch of recursive calls as in DFS lets you compute what is the minimum entry time that you can reach from that vertex. Because it's 2 and it's greater than 1, it's a breach. Now let's take a look at a different example. This is not a breach because you have subtree, but then you have an edge from that subtree going to vertex with entry time 1. Now 1 is an ancestor of 1, right? So what it means that because you can reach the vertex 1 in a different way, not going through the bridge, there is a cycle, specifically this cycle. And it means that this is not a breach. And I encourage you to figure out like the specific details, how you want to store this. A minimum entry time reachable from each vertex. Do you actually want to store them just in an array and recompute them with some recursive formula? You make recursive calls. You now know the minimum time reachable from all children of this vertex. And you just say that minimum entry time from that vertex gets minimum of current value and value returned by DFS, or not returned by the value that DFS computed. More or less in the same way you can find cut points, and cut points are the points, I believe, that disconnect. Right. So in this graph, like more or less all points are cut points except for this one. Not particularly interesting. So yeah, again, a cut point is a point that you remove it with all edges that go out of this vertex. So you remove all of this and your graph becomes disconnected. And the only time when it doesn't is when we remove this two edges and this vertex. And you can find them basically based on the same condition. You just have to be like more accurate about equality cases. So yeah, that's another thing that you can do with DFS. There's also a thing called topological order or topological sorting. It's about directed graphs. And Yeah, I hope this thing with bridges was more or less clear. If it wasn't, then you probably want to look at the implementation. And I'll put a bunch of useful links, the links that I use to study DFS. Like, it was a while ago, but they're still useful. So yeah, again, in this case, we want the graph to be directed. Let me quickly recreate the same structure. I can actually add this edge, but this is not what we want. Let me add this edge. This edge, they're a bit different. I believe this is a cross edge and this is a forward edge. I don't actually want back edges. So that's more or less what I want. Topological sorting is a problem in which you want to assign numbers to vertices in such a way that edges always lead into vertex with a greater number, I believe. So if you were to number just like that, it will be wrong, right? Because so this is just an order that DFS can produce, and it's wrong. And one way to fix it is to look at the exit times, I believe. Oh, okay. So you actually, let's again compute our entry and exit times. Yeah, let's say we went to this vertex first. No, sorry, I'm distracted a little bit. 14, 15, 16, south, 18, 19. Okay, so one possible way to assign numbers is to assign them based on the exit time. So we tried to assign based on the entry time and it did not work. Let's say we instead assign based on exit times. So currently, all edges lead to a vertex with a smaller number, but you obviously can like put, take a negative of each number and it will mean that all edges lead to a vertex with a greater number. So in this way, we found out that time in order is different from reverse time out order. And the second one is called topological for whatever reason. We don't want to get into specific details. What does it have to do with topology? It just called so. I think one possible, no, okay. I don't want to say anything because I most probably am wrong about this. So yeah, it's called reverse order of out times. It's called topological order, and it's useful in strongly connected components. In strongly connected components is another concept about directed graphs. A strongly connected component is like subset of vertices such that each vertex is visited from each other vertex. So basically you have a cycle and then something. But we'll need some more examples, different example actually. Let me have a graph like this. And potential like this, and then probably like this. And then let's say I have a cycle here. And I have edge like here, and well, I'm probably like edge here. Another cycle here. Let's say that here actually I have a bidirectional edge. It may happen, right? And I also have like an edge somewhere here. So as you can see, I deliberately made strongly connected compounds clearly visible. We have 3 strongly connected components. They may have more edges inside of them, it does not really matter. We can have such edge, I don't know. Doesn't really matter. Once we have a cycle, like everything is reachable from everything else. We can actually have something like this, just to make things more interesting. And one property of strongly connected components is that you okay. This is like the definition is the most important property. We won't talk about other properties because they're more advanced. So suppose how do we find this R direction, these components? It turns out that we can do the same DFS. For example, we go here, we then go here. We then can go here, we can go here, here. Maybe we were not that lucky, okay? Maybe what happens if we start here? Because we don't know what is like this first connected component, right? So you may ask, like, what happens if we start here? It's a good question. We will end up in a situation like this. And notice that once we get like interconnected, strongly connected component, we process it entirely before we get back. It's important. So, for example, because we did not know like the root, it means that we sometimes may like miss something. And previously we knew a root because we could select like a vertex with no common edges, but here each vertex has common edges, so we have to be smarter about that. So suppose we did not visit everything, that we just looping through vertices. Each time we see not yet visited vertex, we start another DFS from it. This is again a DFS series. Get something like this. Let us again erase and ignore all entry times. And now let us make the following observation. If we start DFS, another DFS, from vertex with maximum exit time, it will visit only this connected component, strongly connected component. Why? Because the property that we stated, like once we enter the connected component, we visit it entirely before we get back. And I sometimes drop the word strongly connected component. I believe you will realize by this time. So again, if we have one connected component and other, and or maybe even one more. Does not matter like which component you start in first. If there is such edge from one component to another, then all exit point times here will be smaller than all exit times here. Because once you visit it, you process it entirely. Before like going back to that component, like here, or before just starting another DFS here, right? So if you have two connected components, strongly connected components, one is reachable from another, then here all exit times will be smaller than all exit times here. And it means that we can take topological order, reverse it order. And when we start the DFS from here, it will visit only these components. When we start DFS on transposed graph, so we transpose all edges to make sure like we don't exit this. So we take reverse topological order and we run a DFS on transposed graph. We transpose graph to ensure that we don't go out of this connected component. We know that it's the most like important one because the exit times are the greatest. So if we were to start usual DFS, then it would just visit everything. But on the contrary, we want to visit only this connected component. So that's why we run DFS on transposed graph. Transposed graph means that we take every edge and invert it. So if it was going from U to V, now it goes from V to U. This way we visit only this connected component, then we go to the next unvisited vertex in reverse topological order, then run again DFS on transposed graph. It won't visit this because this is already visited, so it will visit only this connected component, strongly connected component, etc. So to find strongly connected components, you want to first compute exit points with a series of DFS. Then you want to in reverse topological order. So that's it, from greatest exit time to smallest exit time. You want to run a DFS, series of DFS on transposed graph. Each time you start a new DFS, you get new strongly connected components. And all vertices that you can visit from that start are in that connected component. And it's pretty much all the theory that I wanted to talk about. Like in the gym that we are referring to, the first problem is like quickly determine whether or not one vertex is ancestor of another in a tree. So you're given a rooted tree. You want to check quickly that one vertex is ancestor of another. If you watch our video on lowest common ancestor, then you already know the solution. And we also mentioned it in this video. You just want to compute entry and exit times and compare them. Second problem is find cycle in directed graph. You just need to detect back edge. For that purpose, you need colors. Third problem is find bridges. Fourth problem is find cut point. They are mostly the same, like one line differs or maybe two lines. When you have to be careful with equality case. Fifth problem is to find strongly connected components. And sixth problem is to build a condensation of the graph. In condensation of a graph, it basically takes strongly connected components. So you say, hey, your entire component is now a vertex. So a condensation graph would be like, you take this, you take this, you take this as a new vertices, and you draw whether there is such as. Yeah, there are two such edges, but we only draw one. There is such as and there is such as. And notice that condensation of a graph is always acyclic, so it does not have cycles for obvious reason, because then your connected components would be wrong, right? Strongly connected components. So yeah, condensation of a graph is directed acyclic graph. Oh, sorry about this. Hey, stop. Damn, man. I'm trying to make a video here. Stop. Okay, sorry. I mean, it's a close friend of mine, so I don't turn off the notifications, but apparently something bad happened and I have to. Okay, okay. Yeah, he got something interesting he wants to show me. Okay, it's okay. I think this is it for the theory video. To find a condensation, you just want to compone the ID of every strongly connected component for each vertex. Like, what is the ID of the strongly connected component that this vertex belongs to? And then you just take a look at all edges and just say, like, hey, you go to this connected component, you go to this between these strongly connected components, you're between this. And if it's a loop, then you just don't draw it. So there are no, in condensation of the graphs, there are no such loops, self loops. Yeah, this will be it for the theory. But implementation we'll have a separate video because like it's very easy to implement each of these algorithms with versions. You write a new DFS and you get everything working, but in fact, it's not a good way to implement this. And I want to talk about specific pattern in programming, I guess in object-oriented programming, that makes the implementation of all these algorithms look very similar. So you write DFS once, and then you write something else instead of DFS that makes use of DFS. Yeah, I want to go like in greater detail about what is the way to write generic DFS, and it definitely does not fit in time limit of this video. So this will be theory only video. Yeah, thanks for watching. I guess I'll see you in the next one video about implementation. I hope I can record still today, but we'll see like whether or not I can implement everything in the expected way. So yeah, thanks for watching and see you in the next one. Bye bye.